again for having me. And today I want to talk with you about several different ideas that all are connected through the concept of space sustainability and Earth space sustainability. This is a growing issue, and as astronomers, it actually affects us considerably. Now, I work with a whole bunch of amazing people, and I'm not able to name all of them. And so I want to just highlight two organizations that I work with. One, the International Astronomical Union's Center for the Protection of the Dark and Quiet Sky. It's actually a longer name than that. I'm shortening it. But if you want to learn more about some of the things that's being done there, you could use this code. And then the Outer Space Institute. This is a network of researchers all united by their interest in addressing grand challenges associated with humanity's use and exploration of outer space. If you'd like to know more about what is happening there, please take a look. We just recently gave a statement at the United Nations Legal Subcommittee at the Committee of the Peaceful Uses of Outer Space, for example, on lunar coordination. So we're quite active in a number of different areas at international fora at the highest level. I would like to begin, though, with a field. I would like you to picture a farmer's field. And the farmers are getting ready to seed that field. They go out, and one stumbles across this mass of twisted metal, carbon fiber, scorched. Doesn't know what it is, so the farmer takes it back to their barn. Starts talking to other farmers in the area, and it finds out that they also found pieces just like that. So they all gathered into one single barn, looked at the pieces carefully, and determined that the only possibility is that they had found a spacecraft. Now, this might seem like the beginning of a sci-fi, but it happened in Ituna, Saskatchewan. Here are the pieces of a Crew Dragon trunk. This is the non-pressurized component of the Crew Dragon vessel that services the International Space Station and also ferries astronauts to the ISS. It is unpressurized, and upon re-entering, what they had been doing is detaching it well before the re-entry for safety reasons, and they just left it in orbit. And then it would come down at some later time as the upper reaches of Earth's atmosphere finally brought it back down through gas drag. It broke apart, and it scattered deadly debris over, in this case, Saskatchewan. What happened was that through media, eventually the farmers got in contact with SpaceX. SpaceX came up with a U-Haul, loaded the pieces, went into a room with the farmers where they signed various paperwork, and they were paid apparently $5,000 each for the space debris. That's apparently the going rate. And then they drove off, and it was for the storage of the space debris. This is my colleague, Sam Lawler, who actually lives not too far from Ituna. She works with me on space debris, space sustainability, and it's this amazing story in which, while she works on space debris, and space debris hit close to her house. If you want to know more about this incident in Ituna, we wrote a conversation article on this, so please take a look there. I can show this later too. Sure. Tesla. So the Tesla is, as you know, is in orbit, and at someday will probably eventually hit Earth again if it remains from solar radiation. But it will be a long time until that happens. That's another topic that I would be very happy to talk about, but that is not quite part of this story. Saskatchewan was not an isolated incident. This is from a campsite in North Carolina, where another piece of that Crew Dragon trunk came down. While filing for the use of or for licenses for the launch, SpaceX explained to the licensing bodies in the United States that these objects would ablate entirely in the upper atmosphere, burn up. That is not happening. This is in Australia, in the outback. Same object came down. So there is a very big Crew Dragon problem. So every time SpaceX services the ISS, it's dropping deadly debris onto the surface of the Earth. They have been changing their practices, trying to get it so that it will break apart over the oceans. We will see whether that works. SpaceX, though, is not alone in this. This is actually a long-standing issue. And one of the things that's happening is we're simply launching so much stuff now into outer space, we being humanity, that it's really starting to show. But you can see that a pressure vessel from a Falcon 9, and landed, I think this is in Indonesia, for example. This is a connector ring from a rocket that re-entered and landed in India, and it was from a Chinese rocket. This is another pressure vessel. This is just re-showing some of that space debris from the Crew Dragon trunk. And this is a very particular example. This is where NASA gave the okay for the International Space Station to jettison an old battery pack under the assumption that it would burn up entirely on re-entry. So one piece of that battery pack went through a Floridian's house, went through their roof, went through the ceiling, and embedded itself into the floor of their house. Someone was home. Luckily, no one was actually hurt. Now, it's not just actually what we call the casualty risk from the debris falling. It is interruptions as a result of this. So what is shown here, I'm going to go ahead and highlight this a little bit more. This is airspace over Europe. And there's a Chinese rocket body that was going to re-enter uncontrollably, and it was going over very busy airspace. And so the aviation authorities of Europe had to decide whether they were going to accept the risk on behalf of all the passengers of a re-entry of debris or close airspace. In this particular instance, they closed airspace. That came with consequences because not only were flights delayed, but flights were suddenly rerouted. And so it created its own set of issues. But we are now seeing authorities have to make this call. And just within the United States, this happened twice recently with the Starship mishap, 2 Starship mishaps in a row, where again, they had to close airspace very suddenly. Now, Canada is actually an interesting state regarding regarding these reentries, because the Crew Dragon trunk is not the first instance in which we've had to deal with this. So in 1978, a reactor from a Soviet spacecraft re-entered uncontrollably and broke apart over the Northwest Territories and spread nuclear waste over Canada. And so what happened then was a major cleanup effort, which you could see just some pictures of that cleanup effort right here. And actually Canada remains the only state to file then a claim under the Liability Convention, which is one of the instruments under international law dealing with space and sets one of the cores of space law. We'll talk about that a little bit later. But that is its own interesting story. Now, it's turning out that the Crew Dragon trunk, the rocket body, large rocket body pieces are not the only pieces that are becoming of some concern. This is approximately a 2 foot by 1.5 foot, 2.5 kilogram plate from inside a Starlink satellite. This re-entered, can't believe it, over Saskatchewan, and was recovered once again when the farmers went out to the fields. Basically, you have a big flat area. There are a lot of satellites that re-enter at latitudes around 50 degrees. It's something that I can go into in questions and answer, but it basically has to do with the way the orbits are set. And when you take something that's on a orbit and you incline it, you spend more time at latitudes plus or north-south that the inclination is. So if it's a 50-degree inclination orbit, so if I take 50 degrees around, 0 degrees around the equator, 90 degrees around the poles, 50 degrees going up. If you take 50 degrees going up, where a lot of satellites are, that means they spend a lot of time in the turnaround points projected onto Earth. So it just creates a high probability for coming into those latitudes. So that's true for any latitude then. Why Saskatchewan is finding all of this, there's a lot of farmland where people go over it very carefully. And so that's why we think we've observed so much space debris there. That piece of space debris was not known by the Canadian government until SpaceX disclosed it kind of in this file. That was just a kind of this generic report that they put out. A number of us who are working in this area noticed it and tried to find out more about it. My colleague Sam Lawler went on public radio to ask who found it and to send information. They actually got in contact with her. And so she was able to get a lot more information about this. And one thing found out is that they also paid the farmers $5,000 for storage. They FedExed the space debris and lost it. and then recovered it. This actually creates a whole host of issues potential issues under international law. Anyway, I started with reentries because it's a very literally impactful and serious situation. But it's actually only one component of the space debris, of what's actually happening with our exploration and use of outer space. So there are actually a whole set of interconnected issues that we are creating. We have rocket emissions, which dump exhaust into the upper atmosphere. This is the only human activity that dumps emissions directly into the upper atmosphere, both the rocket emissions and then the reentry emissions. There's radio transmissions, which of course provide amazing services and benefit people throughout the world. But those same transmissions can interfere with things such as radio telescopes. Could also interfere with actually very foundational geodesy, where we maintain Earth's reference frame by using radio observations of quasars. There's, of course, sunlight from the satellites that can reflect and not just change the night sky, but also interfere with science. And then, as we've discussed, the casualty risks from the re-entering space debris. And one thing that we will really get into later, orbital debris and pollution of the upper atmosphere. Now, before I really go further, though, I have to emphasize this is a really tricky problem because satellites can greatly benefit human society. They come with so many important tasks and have really advanced what's been possible. Through satellites, we have forest fire monitoring, we have extreme weather monitoring, climate science, marine traffic, verification of treaties. This is incredibly important for global stability. It going down from fisheries to arms control. Even banking relies on satellites for the accurate clocks that they have by necessity, mainly GPS. Remember, GPS is both a position, timing, and navigation system, and the timing component often is left out of that discussion. Of course, the navigation itself, communications, connectivity, farming, and search and rescue. And as some of you know, I flew here today because I am an active pilot, and I found out that many of you are pilots as well. confused which computer I'm using. And so I want to highlight one particular use that satellites have had for a while now. And this is actually a bit of now critical infrastructure for society. So COSPAS SARSAT. This is headquartered in Montreal, and it was created during the Cold War. So this is actually really incredible. It was created by Canada, France, United States, and the Soviet Union. And this uses a network of satellites to facilitate search and rescue operations. And it doesn't matter where the person is a citizen from or which satellite is being used. They work together and they save people no matter what. So in airplanes, you have emergency locator transmitters. You could carry personal beacons. If you're hiking, there are marine beacons as well. There are about 2,000 people who are saved every single year just from this system. And of course, that's on an average. There can be big spikes as well. But with all of these benefits are risks. And satellite systems that are proliferated, which is what we have with the rise of mega constellations, are creating a very rapid change in the way we're using outer space. And with that brings a lot of waste. Basically, what's being done now is that satellite systems have exported the Silicon Valley model of rapid obsolescence, continuous upgrades, always get the new phone, always get the new computer, always get the greatest tech, comes with tremendous benefits because the satellites always have the latest technology, but you're also throwing away a lot of material as a result of that. And it all actually stems to one basic problem, and it's not unique in any way to space, as we simply assume that the environment is too big for our actions to matter. We've done that with oceans and plastic. We've done that with the atmosphere and greenhouse gases. And now we're doing that with outer space, with orbits around Earth in particular, but still. If we take a look over time of the cumulative growth of satellites on orbit, we could go ahead and just plot what that looks like. The dark black line, that curve, shows then the growth of satellites in the catalog. So this is just simply everything that's ever been cataloged and launched. The magenta shows what's on orbit. So this is then showing what's on orbit as a function of time. And then the green is showing what has re-entered as a function of time. So that's cumulative. And what we're seeing here is that around 2019, there's a fundamental change. This is the hockey stick for outer space. And we're having, in the last 6 years, having launched more satellites than in the previous 60. And we're rapidly accelerating that. What's lagging then is all of the consequences of the re-entering of all of these satellites, which are only expected to last for about 5 years or so before they re-enter. And so this is going to catch up, and that's when we're going to start to see a lot of the changes. We can go ahead and take space around Earth and break it up into onion shells. And we could take a look at what that is like in terms of the amount of material per cubic kilometer for every 1 kilometer shell, for every 1 slice of the onion or shell of the onion. The green is showing then the payloads, which is basically active and defunct satellites. The red is showing rocket bodies. These are basically spinning school buses left on orbit. The blue is space debris. This is from material that has exploded on orbit through collisions, through anti-satellite weapon tests, where states have purposefully blown up their own satellites to demonstrate they have the capability of doing so. You have accidents such as batteries explode. There's extreme thermal stress as you go from the day side to the night side, and things occasionally blow up. And so what we now have, these spikes here, these are the Starlink spikes. So we've actually enclosed Earth with an incredible amount of material. And while these numbers look very small, or may appear to be very small, because what this is saying is that at the peak of the Starlink satellite, there's roughly, 10 to the minus 6 satellites per cubic kilometer. Okay, so that sounds okay. That doesn't sound very big. The thing you have to remember is that satellites will orbit the Earth every 90 minutes approximately for these altitudes, which means they actually sweep out an incredible volume for their size. So the interaction radius is actually quite substantial. These satellites are moving all the time to ensure that they do not collide with each other. And if that were to just suddenly stop, then we would expect roughly a week timescale until we would have a collision. It's a rough estimate. This is showing you then some of the amount of space debris that we have. We have about nearly 14,000 satellites, 11,000 are working, and more than half are owned by a single company. Yes. They're not all going in the same direction. So they have many different types of orbits, many different inclinations. Some are eccentric, some are circular. So you have a great variety. And even if you start them off in roughly the same orbit, if they're slightly different, they will precess differently. So just like a top wobbles, you have the orbits doing that too. And so even if they start kind of going in the same direction, you wait long enough and they start crisscrossing each other pretty quickly. So not all satellites do, although this is now being, because of what I'm showing here, the densification of Earth's orbits, there is ongoing discussion whether propulsion is going to be mandatory. In fact, Canada just had a government call, I will talk about that a little bit later, through innovation, science, and economic development about new rules for licensing satellites. And one of the questions was, should satellites above a certain altitude have to have propulsion? And so what does that propulsion look like? For most of these, it's going to be electric propulsion. So this would be where you have something like xenon or some type of heavy gas that you then accelerate using then just electrical fields, and that throws out the particles, the gas particles, at very high speeds. So it's very good for making small adjustments. This won't get you to Mars, at least in that version of it. Well, it could get you to Mars. You just have to wait a very long time to do it. It's all about impulse. Most of them don't have chemical propulsion, which could cause very large changes in a short amount of time. If we take a look at the number of objects that are greater than 10 centimeters in size, there are about 40,000 pieces that are estimated. Again, that doesn't necessarily sound too much, but do recall that if you have a hockey puck in orbit at typical collision speeds, which are about 10 kilometers per second due to the crisscrossing, okay? So it's just a little fast. So 10 kilometers per second, that's the energy equivalent of a few kilograms of TNT. And so if you hit a satellite with something that's around 10 centimeters in size, you catastrophically destroy it. It's gone. It blows up into many other pieces, which could then hit other satellites. So you can have this cascading type of effect. There are over 1 million pieces that are greater than 1 centimeter in size. These are very difficult to track, which means you can't maneuver around them. You just hope you don't get hit by them. And satellites are getting hit by them. It's just sometimes they don't knock out the functionality as the satellite. Sometimes they do. This won't cause a catastrophic disruption. You could just disable the satellite. And then if you go down to 1 millimeter, which just basically is degrading the environment, it doesn't It won't take out a satellite on a single hit. You'd have to get very lucky for that. But it is degrading that environment. And there are over 130 million pieces we estimate of that type of object. Altogether, space sustainability is this confluence of multiple pillars where we have this idea of dark and quiet skies, preserving the night sky. We have casualty risk where we started launching emissions. We're going to end with that. Space security, I'm not going to be able to talk too much about that. Space debris, we're only touching on that. This concept of non-appropriation. This is where you put so many satellites in one orbit that no one else can put a satellite there and operate safely. So under international law, space law, you're not allowed to appropriate a region of outer space, particularly on celestial bodies, but also in orbit by claims of sovereignty, by occupation, or by any other means. And so if you put so many satellites in one particular area, that creates then a potential issue with the appropriation principle. I want to, though, because of this audience in particular, focus a little bit more on dark and quiet skies. So I can say that the first time I had ever truly seen the Milky Way was actually when I was a graduate student, because that's when I was sent to a telescope, a research telescope, in a very dark site. And then I could see it. And it was absolutely amazing to see it. And the reason why I hadn't seen it yet is because I lived in a very light polluted area. And so one of the big challenges that we're seeing with our use of space and what is now being called dark and quiet skies is that so many people live in regions where they've basically lost the night sky, not completely, but they've lost it enough that they're not seeing the changes that are occurring to the sky as a result of all the satellites. Now, with terrestrial light pollution, we are lucky that we can go out to dark sites still. We can find dark skies, and then we can see skies that aren't quite as dark, but are still nearly as dark as what our ancestors saw. And that's an amazing thing to do. And actually, RASC is really important for this because of its connection with Parks Canada and the dark sites throughout Canada, the dark parks for astrotourism. So RASC has a really important role in that. But because so many people have already lost the night sky, they don't realize that they can't simply go to a dark site anymore to get away from satellite light pollution. It's always there by design. By design, the satellites are everywhere to provide services for everyone, no matter where they are on the planet. And so you can't go somewhere to avoid them. In the top left here, this is showing all these blue dots are satellites and rocket bodies projected onto the globe, just showing where they are in longitude and latitude. And you could just kind of see the geosynchronous belt here. And you can see that there's a population of satellites all throughout. But by 2024, end of 2024, this really started to become populated. You can actually see one of those caustics that I alluded to, where you see that turnaround point for the satellites right around 50 degrees. And this is one of the reasons why Canada is going to have a higher proportion of objects falling on it than in many other states. So we can see this change in just a little bit. What's that?
State.
No, national state. Yeah, no. Nation state. State as in all the states in the United Nation, not United States. Yeah, nation states. No, rightfully so. That the United Nations, you refer to, the United States being a state. Canada is a state. The Soviet Union, while multiple countries, was a state, for example. Yeah, it gets confusing too, particularly when you're talking to Americans and you start talking about various states throughout the world, and they're like, what are you talking about? This is a snapshot of the night sky. And for those who were wondering what I was doing at dinner, I was just finalizing this particular plot because I had to grab the data this morning. And this is just a snapshot at 11 p.m. tonight of what the sky will look like at that time in Vancouver. And it will look very similar here. Now, you won't be able to see all of these satellites, okay? Because fortunately, not all of them are super bright, but there are a lot of satellites. And at this time of year, if you go out between 10 and 11, and actually throughout the whole night, starting around now, you will be able to see satellites and they will just be all over the sky. Let your eyes adjust and they will be there. Could talk about a whole bunch of the features that you're seeing here later if you would like. Of course, this is an image of a comet that was exposed for 20 minutes. And if you look at it closely, you just keep seeing fainter and fainter star trails. Excuse me, satellite trails. Satellite trails, Ennis. So, of course, in things like astrophotography, you can just take lots of images and throw away the data that have the streaks in it, and you could still get an excellent image by the time you're done. You will be throwing away data. When you talk about that for $100 million facilities that are operating internationally for astronomical research, throwing away images because of a satellite streak start to become problematic. We already have to throw away a lot of data for other reasons. So you start doing that, that's actually a real time impact. That's a cost impact onto taxpayers throughout the world. And that's a separate issue from just changing the night sky. If you go into outer space and take your images from there, you do not avoid satellites because you look through the satellites in order to keep looking at space. You have to go really far away from Earth for that not to be true anymore. So this is an image from the Hubble Space Telescope, which has 3 Starlink satellites going through it in one image. This then is a depiction. Of course, it's really trying to emphasize the debris, but this is the debris around Earth. Earth is enclosed in a cloud of space debris. So we're not at the stage of Wall-E, if you recall that movie, but it is getting bad and it is going to be affecting operations here moving forward. Radio astronomy is also being impacted considerably. It's a fundamental way we explore outer space, and it's essential for detecting certain type of astronomical phenomena and also for testing certain physical processes. Just looking at natural laboratories that you cannot reproduce in a lab and can tell us about fundamental physics. So radio astronomy is essential for that, but this relies on radio quiet sites. What we've done in the past, and what we've been doing, is that you can go to a region on Earth. Oops, could we go back a few slides? I think I got a little excited. One more. There we go. Yeah, I advanced too quickly. You can go to a place that is a radio protected site, such as the Dominion Radio Astrophysical Observatory. And here you can have controls terrestrially. But when the radio signals are then coming from the sky from satellites, then that can cause substantial interference. And it's one thing if it's within the specific frequency in which they communicate, which is very highly regulated. But what's actually happening, then in addition to the typical transmission, the satellites are noisy. And so they have a whole bunch of unintended radio emission. And that unintended radio emission is getting picked up by the radio observatories. And so this is just an example of that. This is an array in Europe. And as one of the Starlink satellites went through, all the telescopes that had the satellite go through its field of view, what we call its beam in radio astronomy, just lit up with signal. And so this is now becoming a serious issue for radio astronomy. And what may become really problematic for both radio observatories as well as optical observatories, and just looking at the night sky, are the direct-to-cell satellite communications. So now this technology is being put out. These require very large antennas put in orbit. These satellites are very, very bright, both in optical and radio, at least where they're transmitting. And they're looking to put hundreds of these up, again, to cover the Earth to ensure that everyone has cellular service no matter where they go. This is, providing these services be really important. It doesn't mean, though, that we have to provide these, do everything from orbit. And we have to understand that providing those services from orbit come with some pretty serious consequences. So this is then that same projection that I was showing, just going in advance. Right now, there are about 65,000 satellites or so, roughly. The number changes a bit, but there are about 65,000 satellites, proposed satellites, that have over or approximately $1 billion in backing for the company that wants to put it up. So we're kind of showing what we think are the serious satellites here. And if you blanket then the Earth with these satellites, you see these caustics here. This does not show the actual satellite. So this is in addition to the current satellites. You see that you have this concentration of satellites over Canada. You have these other bands where there are, of course, north and south. So again, you make it by design so that there's nowhere you can go in which you're not seeing satellites. So again, dark and quiet skies is just one component of this. There's one more thing that I want to tell you about. Re-entry emissions. So if you have these satellites living for 5 years, because that is the design that's being made, you're constantly reimagining the technology that you could put on the satellites by doing so. So from a tech point of view, it's very advantageous. Same idea as your cell phone. But if we just have 30,000 satellites, each about 1 ton in mass, okay, which is totally feasible with where we're going. On a 5-year replacement cycle, that means 6 kilotons of satellites are disposed of per year. Now, when you dispose of it, you design it specifically so that it demises in the atmosphere. So this is that idea that it completely ablates, and you actually do the work to make sure it completely ablates, because if it doesn't completely ablate, you have a casualty risk on the ground. So let's just suppose that that is true, that they are able to engineer it so it completely ablates. That's 6 kilotons of satellites is built every year, 16 tons of satellites per day. Now, the way I try to approach environmental problems to understand whether we have a challenge is whether the environmental rate is exceeded by the anthropogenic rate. That's my starting point. That's not the whole story, but that's a good, I would argue, place to start. So our satellites, with about 30% of aluminum by mass, will have about 4.8 tons of aluminum per day that we're dumping into the atmosphere under this paradigm. For things like lithium, I'll get to what that environmental rate is. The number is much smaller than that, but it's actually 500 times the environmental rate. What is the environmental rate? The meteoroids. So we have about 33 tons of meteoroids coming in every single day on Earth. That excludes the really big events that bring in tons of mass and really skew that average, okay? So it's about 33 tons. 15 tons per day, that's oxygen. We often forget that rocks are largely oxygen, held together by some silicon, some magnesium, some iron. 6 tons per day of iron, 4 tons per day of silicon, for example, and so forth. Only 0.3 tons per day of aluminum. So even though this number, 16 tons, does not exceed that number, the compositions of satellites are so different from what's happening naturally that for many materials, we are already exceeding what happens from meteoroids. And certainly if we get up to 30,000 satellites, we will be greatly so. What are the consequences of that? Well, we're starting to see this already in Earth's aerosols. So stratospheric aerosols. Recently, basically a converted spy plane went up to the stratosphere and was able to scoop up, so to speak, a bunch of stratospheric aerosols, bring them back to a lab and examine them. When you examine them, this is what they would normally look like. And this is what, at the moment, 90% of them look like, fortunately. And this is all populated largely by meteorite material. But 10% of them had these excesses of aluminum, niobium, molybdenum, lithium, hafnium, materials that should not be in our aerosols, but they're there in 10%. And that's because the satellites are already changing Earth's aerosols. Now, Earth's aerosols are a fundamental component of Earth's climate system. By changing the composition, we have the potential of changing their optical properties. And if you change their optical properties, it changes Earth's climate. We don't know the severity of this at this time, but this is where we are looking, what we're trying to understand. In addition to that, there's such things, this is just a schematic. Aluminum, when turned into alumina, combined with oxygen, it can create particles in which you can have surface interactions in the upper atmosphere that activate what is otherwise inactive chlorine, where the chlorine is attached to some other compound. It frees that chlorine and it allows catalytic conversion of ozone and destruction of ozone. So the alumina is a ozone depleting substance. Now, I want to end though, but there's actually a lot of action that's taking place. And so I want to start with this particular slide. So this is covered a little bit, but it's the International Astronomical Union General Resolution. That general resolution states, viewing with great concern the grave danger that some future space projects might seriously interfere with astronomical observations in the optical as well as the radio domain. No group has the right to change Earth's environment without full international study and agreement. The IAU warns of grave moral and material consequences stemming from disregard of future astronomical progress. And then it urges governments for action. And of course, you'll recognize this really from 1961. Oops, can you go back one more? 1961. So this was actually put forward by a general resolution in 1961 by the IAU because of a space project. And that space project was Project Westford. This is where the United States military wanted to ensure global communications by creating an artificial ionosphere. They wanted to create an artificial ionosphere because the natural ionosphere is too variable and too unreliable. So they wanted to try to make something that was steady. So what they did is they took 480 million copper wires and successfully deployed them in orbit. That created a ring of dipoles. And what they did is they used that ring to bounce radio signals off one site so it could be received by another site. Now, yeah, it worked from a technical standpoint. It was not very practical, and fortunately, they abandoned that project, particularly since satellites, how we think of them today, communication satellites, actually obsoleted this idea entirely. But that was changed. There was a lot of concern for radio interference, for glints that these needles would have for astronomical research, and so the Astronomical Union made that statement. So the copper wire, there are some that are still up there. Basically, they are so small that, I mean, they're 1.78 centimeters. So they're, for space debris, they're not that small, but they're very low mass for their size. And so radiation pressure from the sun, just from photons from the sun hitting it, made most of them very eccentric, and they re-entered Earth's atmosphere as a result of that. But some clumped together on release. And that made them effectively a lot more massive. And those clumps are still up there. Now, that resolution, and it wasn't just astronomers screaming into the void. The resolution, the IAU 1961, was actually noticed by the Committee on the Peaceful Uses of Outer Space at the United Nations General Assembly. And there's a science and technical subcommittee in the Committee on the Peaceful Uses of Outer Space, where they recommended attention to turn to the urgency problem of the importance of preventing potentially harmful interference. This led to Resolution 1962, which was eventually incorporated into Article 9 of the Outer Space Treaty. There's actually a direct connection from the action of astronomers to the founding of space law as we know it. Space law is actually made up of 5 treaties plus relevant international law. We have the Outer Space Treaty, then you have 3 treaties that expand on articles within the Outer Space Treaty. And then there's the Moon Agreement, which often is kind of thrown to the side because it's just not very highly, it hasn't been ratified by many states. There's a whole separate topic. International law and the UN Charter apply to outer space. And one of the big things that international law does in space is it makes states responsible. It also creates a series of vague but binding principles. Those are things such as non-interference, non-appropriation. The Outer Space Treaty actually is one of the most successful arms control treaties. It prevents weapons of mass destruction from being stationed on orbit. Yeah, you could have nukes fly through space through ICBMs, but they can't actually be stationed on orbit. So they can't be put in orbit and just hang over everyone. Moon and celestial bodies are for peaceful uses only, and that exploration and use has to benefit all of humankind. So these are very vague but binding principles. And what it comes down to is the states creating their own domestic legislation to meet their international obligations. And that's where it gets tricky. But there's a lot happening. It's not just this law. There are actually programs. There's the International Telecommunication Union, the UN Environmental Program, and of course, all these different components of environmental law, some of which is applied directly to space. And all of this is growing. And so there is action. It's just a question of how is this action taking place and how quickly is it happening relative to the changes that we're seeing. And one thing that I want to really highlight to all of you as I end is that the IAU General Assembly passed Resolution 1 in 2024. And this actually, again, trying to lean forward with rethinking how we interpret international law applied to space and state responsibilities, nation states, state responsibilities to international law. And that is astronomy and astronomical observations are a form of space exploration. So outer space law actually applies. That's the position. That the night sky is intangible human heritage. And that access to dark and quiet skies is fundamental for research in astronomy. And it is important for public services. And I'm going to go ahead and skip this just to go to this final thing. What can you do? First of all, learn more about this. I've only scratched the surface. I'm happy to talk a lot more about this, answer questions, but we were really only touching a small portion of what's to be discussed. Once you learn more, share what you've learned. I mentioned already the government consultation. That's open. That one was open to all Canadians. They're really looking at what licensing rules should be put in place, and they're looking in a broad way. And if you do the research to understand what's happening, you can write something that's compelling to put into that consultation process. And they are required to summarize it, to basically summarize all of what's been put in for a document that will live going forward. So you can have an impact there. You can write op-eds. If you're in charge of any type of programming, you can incorporate this into your programming. So you can have a space sustainability event run by RASC. If you use a satellite service, totally fine. I use satellite services flying here today. It's essential. But many of them services, particularly if it's satellite internet, give them feedback to let them know that these issues are important to you. They might give you a blanket, yes, we pay attention to this and so forth, but you can really push it on there, and they are hearing this. They know that there is potential issue there for them, for their bottom line as a business. And if enough people are pushing on that, they'll take it more and more seriously. Some are. Take a look at IU Resolution 1 and actually see what's being said and what's called on. One of the things, though, that I think is really hard for all of us to have, and this is part of conversations that you can have with friends who may not know what's happening. This is conversations that, again, you could have through op-eds and so forth, is that we need to start asking the question of how many satellites do we need to provide the services that are required? That's a hard conversation because no one wants to be limited. But we have examples of where we have shared resources that we do actually share and do well in doing so. And actually satellite, one very special area of satellites is an example, geostationary orbits. That is one place that's a very a very fine resource, finite resource, and we've had to have coordination in order to use that for a long time. Problem is the rest of Earth's orbits don't have that. So I'm happy to end here and take any questions. And thank you for your time.
Different from some of the other talks we've had and recently. I've been told to use the microphone, so I'll use the mic. So do we have questions for Aaron?
Seems you've presented a very bleak picture of what's going on. I don't know if I'm going to sleep tonight, but just wondering, it's nice to have all these laws and regulations, but how are they enforceable?
Yeah, no, it's an important question. They're ultimately enforceable through national regulation and national rulemaking. We know that one company is responsible for more than half of the satellites and the biggest change. And now that one company also has a lot of power, and that's creating a big problem for the one state. With that said, there's the rest of the world. And you have places that are actually doing some amazing changes that are really rethinking their regulation and how they're going to enforce that. And they have big markets. So we are talking about Europe, for example. So the European Space Agency is really leading on space sustainability, and there's a very noticeable absence of NASA, for example. The UK Space Agency in particular is really doing some amazing work. What's going to need to happen is that there's going to have to be some type of discussion and actual follow through with regulation in the United States, also a lot with China as well. But these are possibilities. We've seen this before, even in hard times. And so I don't want us to think that it's impossible. It'll just be a lot of work. And so one of the things that I really worry about is having the rules in place before there's a space disaster. We've already had a satellite collision on orbit, but that was Iridium 33 and Cosmos 2251, if I'm remembering correctly. But that was at a time when there was a lot less material on orbit. That was only 2009. Now we have so much more that a collision like that could be extremely bad, depending on where it happens for many other satellites or human spaceflight operations. So we're hoping that action can be taken before there is another space disaster. where we saw amazing action where there seemed like impossibilities was after a natural disaster. And that an example of that is with the Exxon Valdez. So an example of that is the Exxon Valdez. And so the shipping, particularly the oil vessels, did not want to have, the companies did not want to have double hulls because of the expense of having double hulls. And they went on and on about how it would be impossible to do that, how the regulation would kill the shipping industry, how this and that and that and this. And then Exxon Valdez happened, and pretty much overnight, double hulls were required. Started with the United States, and then it went international. And so we know that this action can take place. The question is making it happen before there's a disaster. Yeah. Okay. We might want to refer to some in a little bit, depending on what the questions are, but we could always bring it back up.
Two companies, one Japanese and one Norwegian, they're using wood as structural.
Yes.
This sounds like a joke, but it's actually a really good idea. Wood has all sorts of wonderful properties structurally.
Mhm.
And of course, metal in the atmosphere.
Right.
What's the status with chassis?
Yeah, this is so it's a fascinating idea that's being explored. And kind of when a lot of the work on the deposition of metals in the upper atmosphere came out, they said, oh, well, wood might help with that as well. And so that kind of came out. So the wood was being pursued separate of the issue is what I want to emphasize, because of the, certain woods could have some very interesting properties and could hold up on orbit. One of the challenges that we have, we being humanity, is that we want to have, there are certain problems where you can change what you're doing in terms of the technology that you're using, and it does solve the problem. But there are many in which that does not occur, in which you simply displace the problem, create something new, that what's actually needed is a combination of innovation as well as social change in order to kind of the way you approach the problem. So for the satellite issue, if you take away the metals and now replace it with carbon, you're going to be producing a lot of soot. And that soot then is going to potentially change then the soot layer in the stratosphere if you were to simply replace all satellites with wood. And so you change one problem to another as a result of it. So you are going to have those emissions, and you're going to form different products as a result of the emissions. Some things may be better than others, and it might be that wood is less problematic than aluminum. But it might be just a different problem, and we don't know the answer to that yet.
There was a movie a few years back.
Yeah.
Clooney and what's her name?
Sandra Bullock, Gravity. Yep.
My background is engineering,
Mhm.
physics, that sort of thing. So the glaringly obvious Hollywood physics was a little hard to explain to people,
Mhm.
but you're not going to see something this big coming at you
No,
at 24,000 feet per second.
no.
Because you can't see the bullet that kills you if you're standing, in a war zone. But the cascade effect, and here comes the cloud of stuff moving at 10 times the speed of a rifle bullet. That's real.
Mhm.
And if that doesn't terrify people, and some people I met, oh no, that's no big deal.
Yeah.
It should. What's your thoughts on that?
Well, So debris does create a somewhat unifying area because many states and companies who want to operate in those states, again, nation states, they want an orbital environment in which they can actually operate and provide the services, and they want it to be clean. And so there is a lot of recognition internationally that space debris is a big problem. So much so that there's the Interagency Debris Coordination Committee. There are rules that are moving fast internationally being adopted to even make more stringent space debris rules. Canada went through a process, France went through it, the United States even went through a process and made it more stringent. So like this is recognized, at least within these higher levels. What is also happening though, is that you see that space security element that I had up. You see militaries becoming more and more bellicose in the concept of space being another war fighting domain. And so you see that with things like the anti-satellite weapon tests. So Russia was the most recent to do it in 2021. Basically, we've argued that it's one of the first shots of the second invasion of Ukraine. And that was done just that what they did is they had a ground-based missile that went up and hit one of their old satellites just to show that they could require the ISS to suddenly move the astronauts and the cosmonauts. I mean, they had cosmonauts up there, but they didn't care. Had to shelter in the return vehicles because of the space debris that was produced. This terrified people that one country was willing to do that. Before that, 2019, India did it. China did it in 2007. The United States did it in 2008 there's some complications involved with that one. But then 1985, the United States did that, and Russia did, USSR did it many times. So like you have this recognition that space debris is a major problem, and in some ways is very stabilizing in the sense that everyone loses if you have too much debris.
It's another example of tragedy.
It is very much a tragedy at the commons, yes. But then you have some with kind of narrow timescales in mind who don't care from the same government. And that creates a lot of problems. And I don't have a good answer to that. But for the debris, a lot of people are working really hard internationally to stop that. And I mean within governments itself, not just people shouting out, but people who are making rules.
Bruce? We had a talk some time ago about the idea that all satellites that were sent up would have some sort of power to sort of come out of orbit, burn up, and that would sort of help with the problem of space. They would sort of linger up there.
Yeah.
Done, they come down. But then you started off by showing all these.
Yeah.
So what is your thought about that as a useful solution or one of the?
Yeah. There are actually several components to this. One of them, what you're bringing up, there's a difference between a controlled reentry and an uncontrolled reentry. So a controlled reentry is where you have something like chemical propulsion, and you're on orbit and you do a burn. And basically you take let's just say it's a circular orbit, and you do a burn and you create a perigee that's at 80 kilometers. And you time it so that it's right over the ocean. That's a controlled reentry. That's the best thing you can do at the moment. The uncontrolled reentries are where you don't have that capability or you choose not to do it, which is often the case. And that is where you just allow gas drag to do its thing, or maybe even you use propulsion to lower the orbit faster to get it out of the orbital environment and re-enter. But then that's an uncontrolled re-entry, and that's when it comes down wherever. Tying it back to kind of cleaning up orbit, some of the regulation that I was talking about, what was the case was that there's this 25-year rule that at the end of the lifetime of a satellite, it needs to be deorbited in 25 years. So one, that's a long time. Two, there's it has very it had a too low of a adherence to make it useful. But what states have been doing is they've been rewriting the regulation, including the United States, to drop that to 5 years. And hopefully, they're also looking at greater penalties that can't just be waived off if you don't comply. And so that's one thing. Now, that's just bringing stuff down quickly, whether it's controlled or uncontrolled, but it's kind of this better practice of keeping things clean. There's the third component is debris remediation, and you have active debris removal. And so this is not useful yet, but in the future it can be. This is where you send up satellites, and the satellites are tasked to deorbit derelict satellites. Now, this is a huge challenge because some of the things that you want to bring down are the most massive. They've been up there for a while. They're spinning wildly. And you have to try to not just rendezvous with it, which actually today is not that difficult, but you have to rendezvous with it, capture it, and then deorbit it. And that is really hard. But active debris removal is a place where people want to go to help with the debris problem. It can't be a solution on its own. It has to be part of the solution, but not on its
Part of the debris removal is targeted at removing large chunks.
That's right. That's right.
And the problem with launching satellites is that the top stage of the rocket that launches it is always larger than the payload.
Yeah.
And it always ends up in orbit because it's taking satellite orbit. Are those rocket bodies routinely deorbited as soon as they release the payload?
It's becoming more so that they are deorbiting it. So right now we have over 2,200 abandoned rocket bodies for these, what you're just articulating. And those are just in orbit. And there are a lot more, well, there are many that also come down uncontrollably every year. But we are seeing a rise in the fraction that are brought down controllably. And this is what I was referring to with the controlled reentry, where you have then you have engines that reignite and bring it back down. And so that can be done. The technology is there to do it. You actually don't have to have the stage go into orbit depending on what the actual orbit is. You can have a suborbital launch even for what launches the satellites, and then when you release them, you have then the satellites are actually able to do a quick raise, which is a lot of what Starlink tries to do. They do have an orbital stage, but there are designs in which you could do that, in which you have a suborbital release, and then you have a short boost with something that's much smaller. So there are different possibilities, but there's not enough controlled reentries. It's increasing, but it's also insufficient.
Excuse me for my simplistic thought here, but I'm just thinking of the concept of all these satellites out there. Okay, so we bring them down. At which point does the capacity of bringing this junk down to Earth become a problem of what to do with it, where to store it? Dump it in the ocean?
Well, most of it is dumping in the ocean for now. And at the moment, that's the least problematic. I say it like that. It's the least problematic of the choices that we have. Just because the tonnage that has, been put into the oceans from other things, which is a separate issue. I'm not defending it. I'm just saying comparatively, space dumps have been small. Now, there are toxic fuels that have been used, but those are being phased out, fortunately. So that's going to become less of a problem, but it is still something to worry about. But dumping it into the ocean is one. Having it ablate into the atmosphere is another. But every single one of these creates another problem. And so you have these interconnected challenges. And so that's why one of the things we have to have is this discussion on limits on the number of satellites, because then you control the rates, you control dark and quiet skies, you can have better space traffic management, but people don't like being told that they can't have as many satellites as they want. So there is a concept of a circular space economy, and that is where some people do want to go. And there are some very amazing people who are advocating for that. We're not there yet, but that's definitely where they want to see, where you are reusing things on space. That yeah, you can have new tech and so forth, but you swap things out. You try to have on orbit servicing. All of that though is going to create then some interesting complications for dark and quiet skies too, because you know, seeing the ISS is pretty cool when it goes over. That's a really neat experience. If you have 100 of those, maybe not such a cool experience. You had a question for a moment, and then I'm not yeah. It's of the current situation, it's the least bad of a bunch of bad choices.
International bodies get together to talk.
Yes,
Talk about dark and quiet skies.
for example, yeah.
Have you ever discussed maybe trying to get all these countries to get mandatory lighting?
So mandatory cutoff lighting for terrestrial light pollution or for orbital light pollution? So the distinction there is that except at borders, light pollution is seen as a domestic problem. And so it's not, so it doesn't have that. So of course there are international bodies that advocate for it internationally, but that doesn't necessarily reach to the same levels of agreement because it needs to be entirely like, you know, done from a domestic point of view. The for orbital light pollution, it's in an area beyond national jurisdiction to begin with. So it's inherently an international problem. And that's the distinction between the two. And for that one, the IAU has made recommendations on limits to the brightness of satellites. And some companies are trying to follow them. I mean, they haven't succeeded because it's hard. It's hard to make the satellites dim enough. Basically, we're saying you shouldn't be able to see the satellite with your naked eye most of the time. And that's hard. So a lot of this, all electronics ultimate, I want to distinguish between like you have the communication aspect of it where you have the uplink, downlinks, and yes, that's all done with radio waves, although they are experimenting with optical links. And you do have laser links on orbit. Oh yeah, they're going through your body all the time, but well, actually the local radio transmission is very high. And so like in terms of like what's going through you, that's not the risk to worry about. That's just of all the risks that I've talked about and so forth, that's not one of them. It comes from very sensitive equipment that's trying to monitor, you know, things from the beginning of, you know, time as we know it, right? And so, you know, it's no, yeah, that radiation is not any radiation to concern you. No. It's all for the instruments.
So you haven't talked about space tourism.
Oh, no, I haven't. No.
See, Jeff Bezos.
Yes.
His wife and all her girlfriends getting all made up, getting their heels on,
Yes.
heading up to space. What do you think about that?
Oh, well, yeah. Do you mind actually bringing up the slides again, please? So this is a book that I co-authored with my friend and colleague, Michael Byers. He's an international lawyer. I'm an astrophysicist. Naturally, we work together. But one of the things that we did is we actually looked at things such as space tourism, and I will speak more on that in a moment, but we talk about that at length in this book. It is actually, we paid the open access fee for it. So while you're welcome to buy it, you can also just download the PDFs and read it. So please take a look at that. But yeah, so space tourism, basically it's an extremely dirty endeavor, you know, for a small group of people to partake in. And so every rocket launch, you know, just has a tremendous impact on the environment proportionately for the single act. And certain things are really bad. So I think one thing to try to think through is that while we live in the troposphere where there's a certain chemical composition, there's a certain abundance of materials that we're used to, and that is very natural. And there are things that we think of as being green that in the troposphere are very green. That is not, you cannot take that as inherently true for any other level of the atmosphere. So Blue Origins uses cryogenic propulsion. So one of the products, not the only byproduct, but one of the byproducts is water. So they launch this rocket that goes to 100 kilometers. People joyride in it. They go, "Oh, the Earth is so lovely. I didn't know that before," and come back. And they say, "Well, it was water, so it's not a big deal." But water in the upper atmosphere is a foreign substance. That is very peculiar. And so that changes the, you could have mesospheric cloud formation as a result of that. It has astronomical effects. If you have it in enough abundance, there can be global circulation effects that can come from that, but it has to be a lot more than what we're seeing right now. But I use water just to emphasize that while that is probably one of the least bad, it's not green in the way that we normally use that term, because it's just, the chemistry is just fundamentally different in the upper atmosphere from what it is in the troposphere, because the abundances are different and the interactions are different. And so space tourism, it is an environmentally expensive act for few people right now. And so I see it as, at this time, problematic. I think we'd have to fundamentally change how we do it to make that possible in a way that actually makes sense.
Doesn't the water just fall back down?
Well, eventually it will come, these materials, you have certain mixing areas. And so sometimes it could get mixed upward and leave that way. It gets broken apart into oxygen and hydrogen. The hydrogen escapes. Sometimes the water comes back down, but it's its resident time. In order to fall to Earth, it has to go through the layers. And so you put it up there and it stays up there for a while and it comes down. So, and once it gets down in the troposphere, yeah, it's fine.
Like dioxide, which can have a greater effect on changing the climate.
So it is a greenhouse gas. It is, absolutely. Here I'm more worried about potential changes to things like the cloud and consequences as a result of that. Just because of the high abundance in the troposphere that acts as the greenhouse gas. Of course, water is a very interesting, because it both changes the albedo of Earth, as well as It's part of the carbon silicate cycle, and so it can sequester other greenhouse gases. And so water is a very interesting thing to talk about. We're very lucky we have it. So while it is a greenhouse gas, it's complex. It has a lot of other things to consider. And very, very interesting properties, absolutely.
Okay, well, I think it's, so thank you very much, Eric.
You're welcome.
Really-